So this is my Lab 6 Magnetic Braking with Faraday by Harshan Vijay. I'm in Section B, Martin Morigal's class. So the introduction of the lab, the purpose of the lab is to create computational models of magnetic braking using GlowScript, using experimental data and computational data to compare results between different models, being able to create and do an experiment that shows magnetic braking and the ability to gather data, collect the time data of the falling magnet and model the interaction and compare the computational predictions. So here are some of the concepts and laws that are used. So the general Biot-Savart law equation is used in the computational models of the GlowScript. We don't exactly use it in the calculations whatsoever. It finds the magnetic field from a dipole when it is not on axis or is perpendicular to the center of the dipole. The concepts that we use are Faraday's and Lenz's law, which an induced current will produce if there's a change in magnetic flux. The negative sign in this formula indicates that the magnetic sign will be opposite of the magnetic flux, the Newton's second law and Newton's third law, and these two equations and the change in flux equation, which will be used in the GlowScript code. So preview of the main results, the average time for the magnet fall was 1.67/1.68. Computational model showed a time of 1.286 seconds. There's a 26.5678% difference in the timing of the experiment and the model. So the methods, here's what we did. We basically wrapped a cardboard box. It's pretty simple, uh, pretty simple equipment. We created a metal tube using aluminum foil, used a cardboard box to keep its shape, record its length, inner and outer radius, dropped a magnet through the tube and recorded the time it took to fall through the tube. Repeat this 5 times to average the data points into an average time. The system is the tube and the magnet, the surroundings is everything else. So the assumptions for this experiment was that the magnet acts as a magnetic dipole using the Biot-Savart law. Air resistance on the falling magnet is negligible. The gravity and the magnetic field of an aluminum tube are the only force acting on a magnet. So some of the measurements that we initially recorded for the calculations later on. The length of the tube is 0.465 meters, inner radius is 0.013 meters, outer radius is 0.019 meters, magnetic dipole moment was 3.78 am squared, and the magnetic mass was 0.0023 kilograms. The data for the trial is 1.8 as shown, and the average was 1.68 seconds. Some checkpoint questions. Why can't we use a ferrous tube for a steel pipe? The magnet won't be attracted to the tube and would fall much slower or not that much at all. This skews the results and can lead to potentially no results. What happened to the magnet? How does this compare to a magnet falling in a free space without a tube? When a magnet falls in a free space, there are no forces that prevent it from falling besides the force of gravity. This changes when the magnet falls through the tube because the tube is conductive and experiences resistive forces that oppose gravity, making it fall more slowly. So here's some of the code. So initially the code is for the constants and the variables that we recorded initially. Here are some constants for the delta t, and then as you can see, as we go on, we're creating a gravitational vector that calculates the magnetic force from the tube on the magnet by using the Ring's current. We're calculating the magnetic force on the magnet that finds the net force, and we're using the second law to find the position. As you can see here, we use t equals t plus delta t with the position of the bar of the tube. Then we include the gravity equation and the current on the tube, the charge of the current on the tube, and then using that true or false equation, we're then calculating the velocity, the magnet, and the net force, and then using the bar position, we add that plus the delta t, and then we find the exit minus the exit and enter time, and then that's how we're graphing. The results of the code are this graph, which creates the red and blue, which are the sort of the poles, the north and south end. This is sort of the graph that was created using our velocity and time graph. So results and conclusions, the protocols indicate that the coloring of the tube is an indication that the magnitude of the current is flowing through each ring. Red versus blue, the current flows in opposite directions. So a few potential sources of error can be that the errors from the value of the mu from the lab 3 can be errored. Human error, mistiming of the magnet through the tube can also be an error. So some other results and conclusions are, for the first question, we talked about the intensity, and also talked about which color responds. So this is sort of a shortened answer, so because didn't want to type out the entire thing. So which color corresponds to the clockwise and counterclockwise current? So the red shows a clockwise current, the blue indicates a counterclockwise current because of its resistance against the magnetic flux. So what happens to the dynamics of the system when you flip the magnet around? This would not change the velocity or speed, but would change the direction of the current, so it would flip that around actually. So what does the total time in tube of the real world system compare to the computational model? The time in the tube of the real world system is longer than the computational model, but this may be due to the human error in our experiment. How does the shape of the velocity versus time plot show you about the forces acting on the magnet? The shape indicates that there's an imbalance in the forces, so the constant velocity causes an imbalance as the magnet increases in velocity. So the discussion question is: what if the resistivity of the conductor were reduced possible as close to zero? The induced current must be larger, so the magnet would therefore take a larger time to fall through the tube. What if the holes or slots were cut into the tube? How would this affect the ring currents in the model? If holes or slots were cut in the tube, the magnet would drop faster because the magnetic force, and induced current would decrease because of the lost surface area of the tube. So some of the conclusions from the experiment are that a magnet falling through a metal tube will feel some magnetic force that opposes gravity, causing the magnet to fall slower than expected. The magnet falls faster at the ends of the tubes. Flipping the direction of the magnet dipole flips the induced current direction. And yeah, that's my lab.